Hi everyone, and we are back, and we are going to go through our Pset 6 solutions. The first of our two kind of solid mechanics, mechanical behavior materials problem sets, or focus ones. All right, which material is stiffest? Stiffest is the highest slope. I would basically say this red is our stiffest, so our red one. Toughest is going to have the largest area under the curve, assuming we have the same volume of material. So this has quite a bit of area under the curve. This may be something, but this is pretty high. So I would, usually when you're kind of looking for more ductility, you're going to look at quite a bit larger strain. So I would say probably the red curve again. This may have enough, but it's a little bit tough to tell, but either of those answers will be good. Strongest in UTS, ultimate tensile strength, will be this red guy again. Highest yield strength, again, also I would say probably this is the yield strength about right here, also red. Most ductile, definitely going to be this one. Most brittle, that will be this curve right here. So because the strain falls there. For the red curve, indicate the quantitative value of failure of strain, failure stress, yield strain, yield stress, ultimate tensile stress. So let's go ahead and look. So for the red curve, my strain at failure will be right here, about 32%, let's say 32%. My ultimate tensile strength, my failure strength will be about here, 375 megapascals. My yield strength, which we just kind of did, let's just say it's like 280 megapascals. My yield strain is going to be about 10% right here. And I believe that's all the questions. Fantastic. All right, let's get on to number 2. The red curve from the sample seen below, or the red curve is created from the sample seen below with a thickness of 500 millimeters, a length in the 2 direction of 5 meters, and width in the 1 direction of 100 centimeters. The sample was pulled in the 3-3 direction uniaxially. Answer the following questions below. When a stress of 100 megapascals is applied in the 3-3 direction, what is the force applied for this sample? When the stress is applied, what will be the final length in the 3-3 direction? What will be your estimate of Poisson's ratio for this problem? Write out the full stress and strain tensor when a stress of 100 megapascals is applied in the 3-3 direction. So let's first, I want to look at some material properties. So let's just say I'm going to give a rough estimate. Let's say that that's my slope, or purely linear here. So like we said, right before my yield strain, I'm going to pull out my Mathematica real quickly here, and let's go through what this problem's asking us to do. So just take our little time. Don't be worried about it. So I want to estimate first. I need my material properties. I need my Young's modulus for this system. So I'm going to see or measure. So basically I'm going to get my y red is equal to, so let's say 280 times 10 to the 6 divided by, not 380, 280, divided by, let's say, approximately 0.01. Why am I doing 0.01? Because I don't want percent, I want that. So it's about 28 gigapascals. So maybe a kind of a less compliant or less stiff metal. So red curve was created. So I have a stress of 100 megapascals applied in the 3-3 direction. What is the force applied? So if I'm applying here in this direction a stress, so my stress is equal to force per unit area. So my stress is 100 megapascals equals force over the cross-sectional area. What's my cross-sectional area here? Well, I'm told that my thickness is equal to 500 millimeters. I'm told that my width is equal to a width in the 1 direction of 100 centimeters. 100, oops. That's 2. And then I'm told that the length is 5 meters. So I need to solve 100 times 10 to the 6. Set it equal to force divided by my area here is going to be basically my length times my width, because that's the width in the 1 direction. Solve. So it's going to be 500 meganewtons. Yep. So there we go. When this stress is applied, what will be the final length in the 3-3 direction? So we can actually look at that right here. So if I look at my curve here, if I apply 100 megapascal stress, this is going to be, my strain is going to be about 5%. So the strain is equal to 0.05, which is equal to my, basically, my L final minus L initial over Li. Li in this problem, we know, is, if I'm pulling in the 3-3 direction, I'm looking at my, basically my thickness, changing dimensions. So if I look at that, I'm going to solve that 0.05 is equal to Lf minus thickness divided by thickness. That's my initial length of thickness. So voila, that'll be my, basically, the change in the length there. So you can see, or thickness right there. So let's look at T initially. So T looks like this. So we're lengthening, makes sense. Very good. All right. What will be your estimate of the Poisson's ratio for this problem? So what type of material could this be? So we defined, or actually we already kind of said that this is going to be about 28, 30, gigapascals. So you're not quite up to aluminum just yet, maybe a little bit. So really anything that's 0.3 or 0.4 would work. I'm just going to say that this is going to be a kind of a softer, I'm a polymer person, so I'm going to go, but I would say this is that if it is a polymer, it's going to have to be quite a brittle polymer. But I'm going to go with polymer. So 0.4. And then what would be the full stress tensor when a stress of 100 megapascals is applied in the 3-3 direction? What will be the final length in the 2-2 direction? So we're going to write out the full stress and strain tensor. So when I have stress, I'm only applying stress in the 3-3. We already know what that is, which is 100 megapascals. So everything else here is 0. There's no more stress applied. For my strain tensor, there will be a strain in the 3-3, which we already know. That's going to be the equals to the 0.05 when 100 megapascals is done. But we don't know what's the strain in the 1-1, what's the strain in the 2-2, which will occur. Everything else is 0. So how can we solve for that? Well, we're actually really over-constrained here. I'm going to say nu is equal to 0.4. So we got that. My E33, I'm going to say is equal to 0.05. We will have strain in there. I'm going to say sig 1-1. Sig 1-1 is equal to 0. Sig 2-2 is equal to 0. Sig 3-3 is equal to, not set equal to 100 times 10 to the 6. So I'm going to do my old friend E11 is equal to 1 over y red times sig 11 minus nu times sig 22 plus sig 33. And I'm going to do this over and over and over and over and over again. So E22, E33, sig 22, sig 11, E33, 33. I'm going to do sig 11 and then solve for E22. And it does not want to tell me what that solution is, but I could just get rid of this guy because I'm over constrained here. And voila! And it makes sense because they are constricting and they should be the same amount. I was just over constrained in that solution. So voila, there we go. So that would be my strain, but it's asking for what will be the final length. So if I'm pulling in the 2, again, that's my length. So I'm going to do, luckily these are the same strains. So I'm going to do the same thing before, solve. This is my strain, set that equal to, what's my LF minus my initial length divided by length. So it'd be that constricted there. If I pull in the 3-3 and then the width minus width. So there you go. We got it. All right. On to number 3. I'll see you in the next problem. Thanks. Bye. All right. So let's look at number 3. So I'm looking at the section of my chromium handlebars. What does that mean? I know my Young's modulus is approximately 100 gigapascals. My nu is 0.3. Bicycle in rigid
report
system
rotate around
basically 42 degrees. So around basically that. We're basically doing a 42 degrees clockwise rotation. You can kind of see it rotated here. You can imagine it's around the one axis, 42 degrees counterclockwise. As you can see here, so stressing the 2-3 plane effectively. Okay, so we need to, in the stress state here, so we need to write out the rotated stress and strain state, determine the rotation principal stress, write out the stress state, determine the rotation maximum shear stress state, write that out, write out the stress state in the original coordinate system, and the materials actually, again, can't get away from that red curve. So will this material yield under maximum normal or shear stress? So lots of questions we're being asked to effectively consider here. So let's just try to take it step by step. So first I'm going to call this my sigma prime. This is like the rotated stress. So let's write out what is the stress state in this rotated basically stress and strain. So if I rotated this, basically I'm going to have, and actually we can look here. So there's going to be a stress in the 3-3, which is minus 52 MP. This is all in MP. So minus 52. There's going to be a stress in the, basically the 2 direction, which is going to be positive, which is going to be, so 52 times 10 to the 6. This is going to be 18 times 10 to the 3. And then there's going to be, if you look there, we're basically shearing. So you can kind of see here. So if I'm looking at this shear component, for example, and it's in this kind of, it'd be nice to have it in rotated state, but that's why we give you the harder problems. So I'm going to do again sigma ij. I is my normal, so that's 2. J is the direction, that's 3. So 2, 3. And remember, if I'm on the front side, this is going to be basically a negative shear if we look at it in this direction. So this is a negative shear because on my positive side, the side away from me here, I'm going to call that as my negative. So minus 2, 3, so it's going to be right here, minus 14 times 10 to the 6. And then minus 14 times 10 to the 6. So those are my components, everything else is 0. So I'm going to go ahead and start. I'm going to go ahead and we can let's copy in some materials here. So I want to look at here. We have a plain stress state. So let's go ahead. Let's work with this. What we've got here. So I got my C's, T's, all these good things. So I'm going to do. This is my sig prime, which is going to be equal to. Here it is going to be 18 times 10 to the 3. Remember, normal, 52 times 10 to the 6. Normal, and 14 times 10 to the 6. Normal shear. So normal shear, that's my sig prime. All the other stresses are basically 0, 0, 0, 0. And then this is 0 here, this is 0 here. So I'm just looking at that 2-3 plane effectively because we're rotating around there. So that is my rotated up stress state. What about my strain state? Well, I know that my material is chromium, so Y is equal to 100 times 10 to the 9. My nu is equal to 0.3. Let's redefine that. So I can calculate, and actually I already know for my strain, actually I'm going to have to calculate shear strains. So for example, I know, we'll have to work that out. So let's calculate that. So my E11 is going to be 1 divided by Y times, so E11 prime is 1 over Y times, we're going to call this, my sig11 is 0. Actually, we'll call it, let's actually get it a little bit more formulaic here. So I'm going to go my sig11P is equal to 0. My sig22P is equal to this. My sig33P is equal to this. So let's be a little bit more. We'll say sig And then we don't need to care, we just need sig 23p is equal to minus 14 times 10 to the 6th. All right, and then we could just say everything else is 0. So for E11p, it's going to be our good old friend sig 11p minus nu times sig 22p plus sig 33p. And we could just, this is more just kind of calculating now at this point. That's E11p, E22p. E22p will be this 22, replace this with 1, and this will be helpful again. This will be very helpful. Just stick with me, everyone. So it's a lot of calculations, but there's a reason, because we want you to be very, very, very good at this. And I think that's what we got. Excellent. So, but there's also E23p, if you remember, from our kind of equation, which is that epsilon ij is going to be equal to 1 over E times 1 plus nu times sigma ij minus nu sigma kk Kronecker delta ij. If Kronecker delta I is not equal to j, then this disappears. That becomes 0, but we're left with that one. So there's no sigma 1, 2. There's no sigma 1, 3. So those epsilon 1, 3, epsilon 1, 2 are all 0. So all that we're left with is 1 over y times 1 plus nu. And then I'm going to make this times sig 23p. Oops. And there we go. Fantastic. So that is just the first part. Good news and bad news. That is just the first part of the question. So that is the rotated stress and strain state. Now we're asked, what is the rotation to principal stress state, and write out that stress and strain state. So we need to figure out, and this is where I'm going to get my sig prime, what is the rotation that's going to get me to my principal stress state? What does that mean? It means where I don't have any, basically, where I don't have any shear stresses. So how can I do that? Well, I know if I'm going to do just a general rotation, I need to have this T. Actually, let me close out this. It's really worrying me. All right. I need to do T dot my sig prime. And then I can figure out any of these theta c. So there's 3 equations here. I want to isolate and look at the third equation. Why? Because that's my equation for whatever rotation I'm going to do, whatever theta rotation, again, around the 2 axes here, that is going to give me my new value of shear. So let's go ahead and let's find that stress state out. But if you've been cleverly watching the videos, which I know you all have, and you're not just kind of scanning through this, you may have noticed, although I don't know if it shows it, my power's almost out. So before we lose this scintillating lecture, let's plug our power back in. Excellent. So I need to solve what rotation, when does my shear stress value equal to 0 in terms of theta. So I want to do this numerically. And I can see I have a couple of options. So I'm actually going to just pull out this one right here. Why is there 4? Because I have circular symmetry. So I need to rotate from my current state, that rotated state, I need to rotate 14 degrees, 14.162 degrees to be exact, clockwise. I need to rotate that clockwise in order to achieve that principal stress state. So what would be the value then? So I would do T dot sig prime here. So, and then I do slash dot theta goes to this value right here. And at least in the 2, 3 plane, so you see here, this is my stress, this is my new stress, different values than what we've had previously, as you can kind of confirm there. And then you see this is effectively 0. So I can do the same thing and look at, for example, epsilon. My epsilon values was E1P. Actually, I'm going to do E. If we're just looking at the 2, 3 plane, E3P. You can extend this out actually quite a bit. The math gets a little bit unwieldy, so I would just expect you to kind of be focused in on that 2, 3 plane, stresses and strains effectively. But if you want, go further. E23P. So if I do that, and if I do T dot epsilon slash dot theta goes to that same angle, I'll have And again, you see shear stress is 0, shear strain must be 0. A nice confluence of good events. And then you could actually calculate out, again, with these values, you can calculate all the other values as well. So that's it. What about the maximum shear stress state? So if I want to maximize my shear, well, all I'm going to do is take this equation here, and I'm going to take the derivative of this third equation with respect to theta, and then solve. And when I pull that out, I can see this equation right here. So to get to my maximum shear, it should be an additional 45 degrees clockwise from this, but let's prove it. It's always nice to prove things. So if I did this, minus 45. Oops, just like that. Yep, that's correct. So I could take this. I could take, again, from my original stress state, and you'll see here that a couple of things. From our Mohr circle, you see this is maximized, and you see that these two values are at the same point at that center value here. So we've got it. Fantastic. All right. Now, actually, let's see. And then you can do the same thing with epsilon as well. So let's pull this here, pull it here. I should just do minus 45, but it's nice to show it. And voila, a non-zero value here, same value here, because again, in your Mohr circle, whether it's stress or strain, you're going to see that. Fantastic. Right at the stress rate in the original coordinate system. So again, my original coordinate system, I was initially 42 degrees counterclockwise. So all I would have to do is just do this, or 42 degrees counterclockwise, and this would be in the kind of original coordinate sense state. That's my strain. Let's just say prime. Put this numerically, and then voila. So those would be my stress, strain state. All these are the good things. The material is actually the red curve from the first problem. Will this material yield under maximum shear or normal stresses? So let's go ahead and look at let's look at the red curve. So we're looking at 280 megapascals. So 280 is, basically 2.8 times 10 to the 8th. So these aren't going to get the job done. These are not going to get the job done. These are not going to get the job done either. So you can see here we are not going to yield. And you could confirm that also with these values as well. Our strain is very, although we're using a different material, so again, we should be changing our Young's moduli, but again, we can let that one slide just for the moment. All right, that is problem 3 in a nutshell. All right, let's see you on the next problem for number 4. See you next time. All right, now on to problem 4. So we have sample of PET. That is a polymer, so I know my Young's modulus is 1 gigapascal. I know my nu is equal to 0.4. Sandwiched between sandwiched and physically connected to 2 rigid immovable walls. When the sample is stressed, the stress state exhibited a final dimension in the 2-2 direction of 7,000 millimeters, and the force applied in the 2-2 direction, so in the 2-2 direction was 890 kilonewtons, and that should be a negative. That's not a stress, so we'll have to convert that as well. So in the 2-2 direction on our little material. My PET sample, so let's start to kind of put some of these in our notebook. So one of the things I'll kind of stress right now is as you're working through a lot of these problems, I would start to clear your Mathematica notebook because we don't want variables cross-talking. So even if you have multiple notebooks open, they're usually on the same kernel. Even if they're not on the same kernel, you want to be careful. So I'm going to quit everything, and I'm going to say that my L33, the length of the 33, L33 naught is equal to 1.8 times 10 to the minus 3. My L22 naught is equal to 500 times 10 to the minus 2. And then my L11 naught is equal to 8,000 times 10 to the minus 3. All right. So we know that. We know my y is equal to 1 times 10 to the 9th. I know my nu is equal to 0.4. Alrighty. And we are told that the final dimension, so I could solve, so my E33 is equal to the final dimension, the 2-2 direction was, so basically is equal to 7,000 1000 times 10 to the minus 3. That's that. That's my final dimension minus my L22 naught. L22 naught divided by L22 naught. So that is my strain in that direction, because I get a little bit larger. Should get quite a bit, or yeah, I get larger. Hopefully that math worked out. But anyways, I trust it. Because in the 2-2 direction, 500 centimeters. Yep. So we should be good to go. All right. So that's my strain in the, ooh, not 3-3. This is my strain. I'm going to clear that. Because that's going to be the strain in the 2-2. So that's my value for E22. Actually, let's just say. All right, so that is my E22. So we've got that value there, done. Okay, we're also told that the force applied in the 2-2 direction is, so my sig 2-2 is going to be equal to minus 890 times 10 to the 3 divided by, so if I'm pushing in the 2-2 direction, that means I am dividing by my length in the 2-2 direction times my, let's see, I'm pushing in there, length in the 2-2 and the thickness L33 naught. So that is my stress in the 2-2 direction. All right, so, and then it's pulling, there is some value of sigma 1-1. So let's look at what's happening here. So we've already confirmed that, let's look at our stress tensor. We've identified the material, we need to look at stress and strain. So I'm assuming that we are basically somewhat well lubricated in this problem as well. But there clearly is a stress in the 2-2, and we know its value, check. There is a, oh, excuse me. Oops, I made a little bit of a mistake. I kept looking in the 1-1 direction, and I kept writing it that way, so my apologies here. So, so in the 2-2 direction, it is 890 here. For some reason, I don't know why I kept doing that, but let me fix that quickly. So strain in the 2-2 is fine. This is not fine because if I'm pulling the 2-2 direction, then I am looking at L11. Something did not compute there. So that's my stress in the 2-2 direction. Excuse me, but that is now. Oops, and I'm gonna almost made another mistake, but we got that. All right, that's my stress in the 2-2. What about my? Is there a stress in the 1-1? For sure, and it should be negative. Will there be a stress in the 3-3 direction? So is there going to be a stress in the 3-3? Because we're told that these are immovable and sandwich physically connected to two rigid immovable walls. So basically I know that in the 3-3 direction, the strain, it's connected. So it's not going to change dimensions. So they're immovable, they're stuck. So the strain in the 3-3 must be 0. There will be a strain in the 2-2 direction, and we know that value as well. There will be a strain in the 1-1 as well, because we're pushing on it. And thus, I would expect there will be a stress in the 3-3. Why? Because there is, basically, even though there's a strain in the 3-3, there may be a stress in the 3-3 here. So we have 1, 2, 3 unknowns, because we're pushing on it here. So it wants to expand, or it wants to kind of pull away from the wall, so there will be a stress on that. So either it's going to contract, or it's going to push in, and then we'll solve for those problems. All right, so let's get at it. So I know my E33 is equal to 0. I know my E22. I know my sig22. So now we can go ahead and solve. So solve E11 set equal to 1 over y. I should have a little script for this. Sig 11 minus nu times sig 22 plus sig 33. Then let's solve for all our little unknowns. E22, sig 22, sig 11, sig 11, sig 33, E33, we know it's 0 because we're attached to the wall, and I think that we are okay. So now we could ask it, say, give me my unknowns, which is E11, sig 11, sig 33, and voila! Does this make sense? So in the 1, 1 direction, we are actually negative. Now this could be because, again, that basically the compression here. Actually, let's take a peek at this here. It could be that the compression here is just still, so negligible and small. My sig11 is actually in the opposite direction. Basically, mathematically, we can go determine that. And then we've got our sig33 right here. So that is our full stress and strain state. So again, that's what we're calculating based on kind of the information that we're given here. If it's really kind of attaching there, you're going to actually flip that sign. So it's kind of counterintuitive from what you were doing previously, but we set those bounds. E22 had to, actually, excuse me, again, for some reason today, I am so bad. Yes, that makes sense. E11 is compressing, sig11 is compressing, sig33 will also have to be compressing because we're pulling so hard here. So yeah, my 1, 1 and my directions are a little bit out of sync today. So full stress and strain state, we got that. What about the rotation to get to principal stress? We are actually already in there because we only have normal stresses. So that rotation is 0. What are my principal stresses? It are these 3 values right here. What is rotation maximum shear? Because we're already in our principal stress state, it's going to be 45 degrees from Mohr circle. What's the value of the maximum shear? Well, we know that basically, if I want to do the full 3D stress state, so I could say, I know that my largest value is this. My smallest value is this one. And then I can then divide this by 2, and that'll be my value of maximum shear. So again, apologies for my mix-up in 1, 1, 2, 2, but you can see now strain in the 1, 1 should be negative because we're compressing. sig11 is negative, and sig33 will be negative because why? Well, again, we're pushing, if you look at the magnitude of these, this stress here is much, much, much stronger, so it wants to expand, so it's actually being kind of compressed in there. So the compressive force has to maintain that 0. But excellent. All right. Okay, so actually, let's go ahead and I want to examine the problem above, but now there is no applied stress, but the temperature is raised from room temperature to 500 C. Write out the full stress and strain state. All right, I like this. I'm glad I wrote this problem, and hopefully I can get my directions in order now. Okay, so basically no applied stress. We're still compressed in this rigid rod. So what's going to happen now? And we need to write out our full stress and strain. So our stress, there's no stress applied anywhere. So no stresses are going to be applied here. So will there be a strain in the 3-3? Still no strain here. Why? Because again, we can't expand in that direction. So actually, there will be a stress in the 3-3 here. Why is there a stress in the 3-3? Because it wants to expand, but it's not allowed to. So what about there will be a strain in the 1-1, and there will be a strain in the 2-2. It's just going to expand out here. Again, at the edges here, we're kind of attached to the walls here. It won't kind of explain, but you could kind of imagine that they're going to be able to expand out freely there. So there will be a strain there. That'll just be the thermal strain. So it'll just be, and you could actually calculate that basically based on our, basically from our notes previously. So you can look up for a polymeric material. We have in our notes what is the typical value there. So remember that even if we have epsilon 1 is equal to 1 over E times basically sigma 1 minus nu times sigma 2 plus sigma 3 plus sigma 3 you also have to tack on the delta T. So it will want to expand, assuming that we have a thermal expansion coefficient that is positive. So for this problem, when there's no applied stress, it's just going to be alpha delta T equals alpha delta T. Excellent. And then we can actually figure out what is the sigma 3. So you can actually potentially solve for that, because I know that my epsilon 3 is going to be equal to 1 over E times my sigma 33 minus nu times sigma 11 plus sigma 22 plus alpha delta t. So actually we can solve for these right now. This is a fun little problem. I'm glad I asked it. I've recovered my kind of lost pride effectively from the previous problem where I kept messing up the sense of directions. But first we need to kind of go back and through our notes and re-examine, and that is what I'm doing right now. What is the typical value for a polymer thermal expansion coefficient? And remember, these are just general, very, very rough guides to thermal expansion coefficients. Obviously, materials, there's always alternate examples. There's always things that aren't going to kind of match up perfectly when you're looking at those materials. But in general, generally speaking, these are some good values. These are some good values to have on hand. Actually, if I could find these right now, that'd be very helpful. Here we go. So, for example, for polymers, you can typically expect, so basically alpha will equal, let's say 500 times, this is a very relatively high thermal expansion coefficient, 500 times 10 to the minus 6 inverse K. So that's my alpha, so epsilon T is going to be alpha times, so I take it from room temperature, so final temperature minus initial temperature, 500 K from my, or 500 C, so basically 500 plus 273 minus 298. That will be my thermal expansion. So that is my ET. That is equal to my epsilon 11, my epsilon 22. And then for my sigma 33, will there be a stress in the 11 or the 22? No, because even though there's expanding, there's no stress applied. It's not constrained. The material is not being constrained effectively anywhere. So, but I can solve that 0 equals 1 over y times my sig 33, which I don't know, plus alpha, or I could just plus ET, and then solve for sig 33. And what do you know? It's compressive, because it wants to expand, but it's compressing it. Great problem, Professor Steimel. All right, now let's go ahead and move on to number 6. So now we're looking at a Pepsi can that is basically, the Pepsi can is 5 inches tall. 5 inches tall. It is 2.2 inches in diameter. It has a thickness of 0.01 centimeters. And you can see the fracture pattern here as well. So immediately, once you hear radius and thickness, first you're going to quit your mathematics notebook. But once you're done with that, you want to immediately say, okay, my radius, I need to see if this is a thin wall pressure vessel type problem. My radius is equal to 2.2 inches in diameter. So my radius is equal to 2.2 divided by 2 times 0.0254 to convert to meters. My thickness is equal to 0.01 times 10 to the minus 2. And R over T, what's that value? Oh yeah, that's a thin wall pressure vessel for sure. It is made of aluminum, so I know that my Y is equal to 100 times 10 to the 9. I know my nu is equal to 0.3. Oops. All right. And failure can be failure can expand, or basically it can extend approximately 12% before failure. So once I know my thin wall pressure vessel and looking at this problem and finding my pen, I know that I can make my thin wall pressure vessel assumption. So I know that my stress tensor will just have hoop and longitudinal. My longitudinal is aligned in the 3-3 direction. My hoop is in the 2-2 direction, and then I ignore everything else. I also know that my epsilon h is equal to 1 over e times sig h minus nu sig l. My epsilon l is equal to 1 over e times sig l minus nu sig h. And we know that basically right before failure, right at the point of failure, I know that I can extend up to 12%. I know that my sigma h is equal to delta p r over t. I know that my sigma h is equal to sigma l over 2. And this epsilon h must be equal to 0.12 because that's where it will fail. So let's start the solving. So sig h equals del p times r divided by t. Sig L equals sig h divided by 2. I'm just going to do del p. I know that my EH equals 1 over y times sig h minus nu times sig L. And then I know that my EL equals 1 divided by y times sig L minus nu times sig h. All right, got that here. So let's get to solving. So I want to solve EH, set that equal to 0.12. I'm going to solve for del P, because you can see that's my only unknown left. Once I have this, that's my del P, I can get the rest of the answers. EH, EL, sig H, sig L, voila. Got it. That's it. Now we have to ask, what's the pressure? We found that. Write out the stress and strain tensors where the stress is maximized, where shear stress is maximized, and what is the angle? We know the angle, because we're already in principle, is 45. And one of the cool things about, we know that our principal stresses are sig H, sig L minus 0. So my maximum shear is always going to be sig H minus 0. Actually, here we go. Sig H minus 0 divided by 2. And voila. Let's get back over here. So it's just basically sig L is always going to be that. Is my fracture pattern correct? Yes. Why is that correct? Because my hoop stress is always twice as large as my longitudinal stress. And that's it. Now let's get to our last problem, which is our beam bending problem. I'll see you then. Thanks. Bye. All right, and let's get to our last problem on this problem set, which is our very, very fun beam bending type problem. So let's go ahead and let's get started with it. So we are dealing with beam bending scenario. First of all, I'm gonna open up our beam bending notebook just to kind of give us some things to take from. Plagiarism is the sincerest form of flattery. No, don't plagiarize. That will be bad. Thickness is equal to 2 times 10 to the minus 3. Our base is equal to 5,000 times 10 to the minus 3. All right. Steel beam, so we know that our y is equal to 100 times 10 to the 9. And then if we needed our nu, we know that our nu would be 0.3. So we need to, and actually the problem is actually we need the basic expression for shear moment, bending moment, maximum stress in the beam, and determine where deflection is maximized. So I want to do all those things by first, I'm always interested in deflection, because I know that if I have my deflection equation, then I can get everything else. And I also know that I need my moment of inertia. Mom equals basically b times h cubed divided by 12 for a rectangular beam. And actually, we can know the moment as well, depending on curvature and all these things. But anyways, all right. So let's go ahead and let's first dive into and start to solve for our kind of bending scenario. So what do we have here? What are our functions that we're working with here? Well, I know that similarly, I'm going to have some function here, y times I to the fourth, which is basically fourth order ODE that we're going to have to solve for, and we need to modify this equation effectively. I is going to be our mom, and then solve for this. We know that I'm going to have, as we can see here, a load applied at x minus L divided by 3. And then this P is going to be basically 50 times 10 to the 3. And then minus basically 1 times 10 to the 6 of, and then this is going to be, so this is at L over 3, so this is going to be applied at the Dirac delta x minus basically 3L divided by 4. So that's going to be my function effectively. I don't know why base, instead of thickness H. Oops. I always get used to R notation. All right, so what are my initial conditions? Well, I know that there must be no deflection at that 0. I also know that there can be no moment, because remember, my moment is related to basically the second derivative of my function. So my moment will effectively be that. So second derivative of my my deflection equation. Excellent. So, and then we also know that at the length of the beam, we'll similarly have those boundary conditions as well. So I can now start to solve, just as we've done here previously, for my values. So I can make some of these assumptions here. I'm going to assume that L is greater than 0. We don't need the P, we don't need the Y, we don't need the I, because those are already defined. And so, I get a nasty looking thing like this, and I could do, basically, look at this equation and do full simplify. So let's see if that helps. So let's do full simplify. All right, and then now let's go ahead and look at the solution, and we could actually plug in for, one of the things that we didn't plug in for, what we should have done, I'm going to replace /.L goes to L, and that should make things quite a bit easier. So this is going to be my solution. Solution is this, and then I can now plot this, and let's see how it looks like. X from 0 to L, and kind of makes sense based on what we have here. A large load at the end, kind of offset there. This is looking good. So what is the question actually asking us? Okay, so, whoops. All right, so we've got our function, effectively. So that is great. So we've got our expression for deflection. So we can also now start to develop those other expressions that we're asked to do. So we know the relationship between our shear and our other functions. So for example, our moment function is going to be equal to minus y times our moment times the second derivative times derivative of basically our solution, x second power. So this is our moment function here, and our other function here, we're going to have to do e times moment times basically this same derivative here, and then we're going to take the derivative of this function as well, and then we're going to do minus, so this is shear mom equals this. So that's our shear moment as well. What a lovely function that is. But anyways, we will get to that. Shear moment, bending moment. What's the maximum stress in our beam? So to do that, we need to remember that effectively our stress is going to be equal to, basically, we know that our stress is equal to minus my over I. We know that value. Y is just basically going to be positive half of that beam, so positive thickness, half thickness, negative half thickness, half thickness. So we really have to find what's our maximum of our bending moment. So why don't we go ahead and plot our bending moment? Plot moment function right here, and we can see when we're maximized right here. So we could actually take this and say, I could do find minimum of my function, and I could search for starting, let's say start at x of 3. So about 3.75. Excellent. Looks about right. So we can plug that in. So I can say, what is my, so this is my moment value. So minus minus, so that's going to be plus this times my height divided by 2 divided by mom, and that would be my stress. If I do minus height over 2, tension, compression, all those good values. Excellent. So that's my stress. And where is the deflection maximized? Well, we can kind of see that here, but we could use the same type of solution. So let's do find minimum. You kind of can't do your derivative here because of those Dirac delta functions, but I could say, let's search around x of 2. Let's say x of 2. Yeah, 2.76 seems to be about right. And we've got it. that is your problem set 6 in the books. So I will see you all on our second half of our journey into viscoelasticity, and I'll see you all next time. Thanks. Bye.